Welcome back. Today we're going to move on. We've been on a long journey. We've started with classical fields. We've talked about quantizing fields in the last semester via the canonical formalism. And then we moved on in this course to the path integral quantization as a kind of shortcut to doing all the hard work. And then in the previous couple of lectures we discussed the high point in some sense of quantum field theory, namely renormalization. How do we make sense of field theories with interactions? We're almost done in the sense of quantizing quantum fields at the perturbative level. There's not much, there's plenty more to do, but it's now turns to the job of hard work of just carrying out computations. And that's something that I'm going to outsource to you guys to do. You work through the exercises of your favorite textbook and do some calculations. That's the only way to gain intuition on the processes of interacting quantum field theory. However, there's one sort of glaring hole, right? We want to, the stated objective of this course was to at least introduce you to all the moving parts of the standard model of elementary particle physics. And there's one field theory that I so far avoided and dodged around, and that is non-abelian or abelian gauge theory. So I haven't mentioned what this thing is, and even worse, I haven't even give you a hint of how to quantize this thing. So that's the objective of the sort of the middle part of this course, is to introduce gauge theories both of the abelian and non-abelian variety, and also tell you how to quantize these things. I'm going to give you two recipes, I hope, by the end of this course. One that works better on computers and one that works better on paper. Now, why do we care about gauge theories? Well, because they're there, right? These fields are really there. We've detected their particles. So we have to deal with them. Now, up to, 50, 60 years ago, they were a mathematician's curiosity, but they really are something we have to cope with. Now, we're going to follow the same route as we always do. We're going to first specify step one, when you're building any kind of theory, is to specify the symmetries of the theory. What do you expect the theory to be symmetric under? Certainly it's symmetric under time translations. That's something that should be in there. It's symmetric under spatial translations. It's symmetric under Lorentz group, under boosts. All these symmetries we know have to be presented by whatever theory we build. But if you are aware that there are further symmetries that your theory has to exhibit, then you better make sure that you can represent those symmetries as well. So you specify the symmetries of the theory, and then you look for you specify the symmetries of the theory that you're interested in. Let's say that the symmetries are captured by some group G. And then, how do you build a quantum theory? Well, you look for projective unitary representations of G, which are local. So it's very easy often to find unitary representations of a group. The group can act on itself. So you get those representations pretty much for free. But are they local? Do they correspond? Because we have this notion that that interaction should be local, and that extra constraint of locality here is what gives us quantum field theory. It's the only way we know, with some exceptions, to build symmetries, representations of symmetries that are consistent with locality. That's what quantum field theory is. And then the usual, how do we do this? Well, this poorly specified process of quantization. So this is the only algorithm we know that I can present to you that presents to you local unitary representations of a given symmetry group. So I have to tell you, what's the difference between gauge theory and other theories? Maybe we've already done this. Well, there is one crucial difference. Here's the difference. In gauge theory, of course we want it to be Poincare invariant. But we also want it to be additionally symmetric under a gigantic group known as the local gauge group. And this group acts independently at all locations in spacetime, all events. So I better show you how I'll give you an example, right? It's probably the quickest way, is to give an example. So this example is almost the simplest one that you could imagine building. The local gauge group that we're going to build is built from this incredibly simple little group called U1. So just to remind you, what is U1? U1 is the set of all complex numbers on the unit circle under multiplication. So it forms a group, has an identity, it's a Lie group, the multiplication is continuous. It's a pretty simple group, and you've encountered it before. Now, the way we want our gauge group to act actually, before I say how it acts, I've got to say what it is. Just strike that out. We're going to come back to that. So what is our gauge group? A gauge group is the set of all assignments of elements of U1 to points in space-time. So that's 1 plus 3 dimensional space-time. And the group, G, this local gauge group, consists of, well, a U1 at every point in space-time. And that is a pretty big group, right? Because we need to specify an infinite number of U1 elements, one per each location for spacetime. So the question we're going to now turn to is, how do we actually want to find representations for this gigantic group G? Well, we have to say a little bit about how G is going to act on, how do we think of it as acting on the fields of our theory. So all of the local gauge groups that we consider in this course will be of the form of some continuous Lie group acting independently at every location in spacetime. Yeah, question? Is there some continuity condition for small g is the question. At the moment, you should think not. You should think of that acting truly independently at each location in spacetime. Eventually, we're going to build that in. We're going to demand that these g's will be differentiable as a function of space-time. But for the moment, just think of it as being completely independent at every location in space-time. No. Think of it as completely independent of space-time. Forget what I said about continuity. All right. So how does it act on fields? Well, I'm just going to pick an example, and then you'll see how it acts on fields. So let's suppose we have a Dirac field in our theory. The quantum field theory that we want to make U1 gauge invariant is a theory of fermions. So a theory of fermions needs a fermion field, namely a Dirac field. So we have this Dirac field, and the way one of these guys acts is according to this. Very simple. Now, if I want to be ultra pedantic, then I would say a representation of that element of the group U1, which is none other than e to the I phi x for some phi x. I said phi, but I wrote theta. Theta x. And there's a reason I did that, because I can change everything and make that an alpha. Okay. So what's alpha x? Well, alpha x has got to be a number in the unit circle 0 to 2 pi, everywhere in space-time. That's how we're going to take this local gauge group to act. So you take the field at space-time location x, and the group acts by just multiplying by this complex phase. Super simple, yeah? All right, well, we come to the big question, right? Can we build at least classical theories that are invariant under local gauge and the Poincare group, right? We still insist on Lorentz invariance. What theories are invariant? Well, you know, we're going to have some problems. Well, maybe it's not obvious what the problems are, but we'll go into these problems in a second. But, you know, I want to stress that this is purely independently. So at every space-time location x, there's another copy of U1 acting completely independently of all the other U1s. Okay, let's try and build ourselves an invariant theory, so one that actually has a hope of giving us, after quantization, a representation of this gigantic mega group. Well, it's a classical theory, so we're going to define it in terms of a Lagrange density. What kind of terms are invariant under this? Well, let's start guessing, you know. Well, let's try our simplest one, psi by psi. That is certainly invariant under this gauge group. This is good, right? You know, we've gone from there being an empty set of theories that are invariant under this group to at least a theory that contains one term, namely psi by psi. It's pretty good. That also works, right? The phi e to the I alpha x just goes through and cancels. But that's a vector term, so, well, you know, contract it with itself and you have yourself an invariant term. Fantastic. So it's starting to look good. We've seen these kinds of terms before. Now, there's just one teeny tiny problem, right? I don't know if you've seen this coming or not, but here it is. What about this one? Now we have some serious problems to cope with. And it's to do with the fact that this symmetry is acting independently for all x. So this thing here is not even well defined. And let's explain why it's not defined. You know, inside here, there's a derivative, yes, d mu. And d mu psi is defined to be, well, according to the rules of calculus, it's a limit of the difference between two fields, namely the field at space-time location a little bit away in the direction of the mu vector from x minus the field at x divided by epsilon. That's what d mu x is equal to. Now, how invariant is this thing? The answer is it's not, right? It's super not invariant. This limit does not exist under gauge transformations. So if we do a gauge transformation, then we get e to the I theta x plus epsilon e mu. I said theta again, I mean alpha. Minus e to the I alpha x. Oh dear. Now remember, I was being very careful to say that these alphas act independently of space-time location. So if I change by epsilon the argument of alpha here, I get a completely different alpha to if I had the original value of epsilon here. So this, for every space-time location, is a completely different alpha in general. There's no sense in which this limit exists. It bounces around. Yep, question?
We always work on the lattice of the space-time, so...
Ooh, that's a good question. Well, that's a good question. So we always work on a lattice, is the question. Yes, we do. We will. In fact, that's one of the two ways I'll show you to quantize gauge theory. But at the moment, we're talking about classical theories and classical gauge theories. And we will there imagine space-time is continuous. I mean, ultimately, you know, if you can find a field which is invariant under this gauge group and is continuous, then that's good, right? You know, we'd want that as a prerequisite because we think space-time is continuous. But when you come to the lattice case, yeah, things do change, absolutely. So I won't talk about that yet, but that comes a bit later. But for the moment, we are wanting to build a theory with a continuous space-time, a classical theory that's invariant under this local gauge group, and that is a continuous function of space-time. So when we have those constraints, then we really have a problem right here. So this is not defined. It doesn't exist. Oh dear, that looks bad. So you can build locally gauge invariant theories. No problemo. They're just very boring theories. The Lagrangian only has terms like psi bar psi or psi bar gamma mu psi squared. I suppose such a theory has its charm. Nothing ever happens in these theories. So the way we deal with this is we're going to introduce an auxiliary field, a helper field, which also transforms non-trivially under the local gauge group. So if you just want to have one Fermi field, or if you just want to have a field, boson field, which transforms according to this recipe here, then there is simply no way to make it dynamical. There's no way to introduce a derivative. Done. The only way to get forward is to add fields. These are like catalysts in chemistry. You know, in chemistry, if you want to get from one reagent to another via some chemical reaction, then sometimes there's just no thermodynamically allowed path between the two reagents. And then, what do? Well, you've got various options. You can heat it up, or you can, give it a kick. to get it over the free energy barrier. Or you can add a catalyst, right? That's something that is not consumed in the reaction but helps the reaction to proceed, that lowers the free energy barrier between the starting reagent and the final one. You've always got this available to you in field theory or in physics, right? If you want something to satisfy a constraint and you can't get it to satisfy that constraint by itself, then add things, add ancillary variables to satisfy the constraint, and then hope that at the end, that if they're not, they have non-physical properties, they're not observable. So that's one way around imposing this symmetry. So we're going to add additional fields which also transform under this G in an effort to build our theory with something that has like a derivative in it so that we can have some dynamics. And the way we're going to do that is to look at this expression here. The problem that we have here with the derivative is that we're trying to compare at different locations in space-time the field, but the field is allowed to transform independently at these two locations of space-time. So but what we got there is an example of a comparator. We're trying to compare psi at x plus epsilon e mu with psi of x. And our naivest comparator, which is namely just take the fields at the different locations and compare them directly, that doesn't work. But there's another way to get around this. All right, we're going to introduce a thing called a parallel transporter. And that's a recipe for how to compare fields at different locations. It's just a number for all x and y for all space-time locations. It actually depends on the path. But I'm going to suppress that dependence on the path for the moment. So it matters how you get from x to y, this way of comparing the two fields. We won't just, this is really suppressed for the moment, this dependence on the path. This, and in order, I guess I'll call it G, invariant. All right, so suppose we could find this thing, this parallel transporter, that transforms in this particular way here. So suppose you could find such a thing. So that under a local gauge transformation, this two-parameter object transforms according to this group element in this very particular way. So suppose you could do that. Well, then you'd have a way to compare in a gauge invariant way fields at two different locations. So we introduce a definition now. You're not meant to understand, you're not meant to be able to prove this, it's really a definition. So we define the parallel transport of x of the field at x to the location y to just be this object here. And so let's check what happens under a gauge transformation. And we see a pretty nice result. So this object transforms exactly as though it was living at spacetime location y. That's pretty cool, because now we have a hope of building something that looks like a derivative. I'll say what that is in a moment, but firstly there should be a question. It's all very well to posit a useful thing, but if that useful thing doesn't exist, then it was all in vain. Well, these things do exist, and in the process of explaining how to define the derivative, we'll actually find a way to build such comparators or parallel transporters. So yes, they do exist, but you'll have to wait. Now, at this point, I should mention, of course, that this is a topic that's received attention from mathematicians for many, many decades. This is an example of something called a principal bundle, fiber bundle, and if you're interested in the mathematical foundations of what we're doing here, you can indeed look up fiber bundles, principal bundles, and learn all the mathematics you need to make this fully rigorous. So this is not at some vague level, some metaphorical level of physical rigor. Everything I'm saying here can be completely 100% made rigorous. There's no need for this course. We don't need to go into all these details. We only need sort of certain elements of this theory which we can derive at this very elementary level. So let's stick with that. But if you are curious mathematically, that's where to look. Very beautiful theory indeed. Now, there's a little air of non-locality about what I've just said. So I've posited the existence of this object u, y, x. Now that's not a field. To specify a u, y, x, I need two locations. So that's slightly non-local. Maybe it's a bi-field or something like that. You know, I began this lecture by saying that one wants a theory that represents symmetries locally. And, well, we found a way to do it, apparently, in a non-trivial way, by introducing this auxiliary object called the parallel transporter. But this parallel transporter looks pretty non-local. I told you that it actually depends on the path between y and x, so it's actually, as it's written there, it looks like some non-local data I've added in by magic. So what I want to do now is argue to you that we can specify these parallel transporter objects using local data. And if we can do that, then we can build local theories which are invariant under this gauge group. But until then, we have a non-local theory. So I just have this bunch of u's that somehow I magically found, and then we were able to compare the fields at different locations. Well, all of this will become clear as we discuss how to define derivatives when we have a thing that we can use to compare things with. Let's look at first derivatives. We're going to introduce an object called the covariant derivative. Let's call it by what it is. It's called the covariant derivative. It's exactly the same as the covariant derivative you find in general relativity, but for a different gauge group. But we'll get to that later. So we can define, this is a definition, right? This is not the derivative, it's a derivative, a different one, the covariant derivative. So we can define the value of the field at, using E. Yes. We can define the field at x plus epsilon mu e mu. But that field transforms independently of psi of x. But this object transforms in just the right way at psi of x. Now, let me just check I did it in the correct order. Wouldn't you know it? Okay. I did it the opposite way around, so I will rewrite this. I may as well be consistent with my notes, because if I'm not, then I'll just keep making mistakes. So psi at x plus epsilon e mu and u x plus epsilon e mu psi of x both transform the same way. Define d, the capital D being for derivative now, mu psi of x is defined to be the limit then, as epsilon tends to naught, of the difference of these two things. Boom, done. It's easy. So that certainly will transform in the right way, because every point along the sequence of terms in this limit, it transforms in the right way. So it's good. It transforms in the right way. So what is it? It's a derivative-like object. It's not the derivative because we have additional data that we've used to define it. But to give a theory dynamics, you don't really need it to be the derivative inside the Lagrange density. You just need it to be a derivative-like object, something that compares things at neighboring locations, so to speak. And so that's okay, right? For the task of building a dynamics into a theory in such a way that it's invariant under this gauge group, this is still a reasonable candidate. Now, we haven't gotten much closer to getting rid of the non-locality, however. The non-locality is there. Look, this u, right? This u is there. And this u transforms in this very particular way under these local gauge transformations. Now, I said the local gauge transformations act independently at each location in space-time. Ooh, maybe u has to depend in a nasty way on these local gauge transformations. So that's not clear. So we're going to have to get around, we're going to cut around finally to the problem of can we locally specify u at all, or is it just purely non-local data? Well, let's be optimistic. In physics, we should always be optimistic, not pessimistic. So let's suppose that we're in the best of worlds, not just an arbitrary, malicious universe, but one where things are really, really nice. Let's suppose that this is really differentiable. It's not only continuous, but is differentiable near x. You know, right? Why not? Right? It could be. So, what does Taylor's theorem tell us if it's nice and differentiable in some open neighborhood around x? It tells us that, well, it's equal to u at xx, right, when epsilon is 0, plus epsilon, some Taylor coefficients, right, d mu. Oh, I forgot x. Where's x gone? Epsilon e mu. There we go. Now it's all good. For a. It's pretty good. Let's be even more optimistic. Let's just try setting uxx to be 1. I mean, 1 transforms in the right way when y equals x, so why not set it to be 1? Then our Taylor series becomes this. I've just given this a name here. Now, it's actually traditional to pull out a spurious constant. Well, not spurious. So actually, to make it slightly less stupid, I will just do that step in one more line. So it's traditional to define the derivative here as minus IE, where E is some constant. You know, what constant is it? Well, it's the fine structure constant. You pull that out because about 10 pages down the road, it's a bit easier. We didn't have to pull this E out. But you were free to redefine A so that's the case. We pull out that IE, and then we end up with this expression. All assuming that this bizarre parallel transport, a non-local object, is differentiable. All right, this A is not arbitrary. It has to satisfy some constraints. So the first thing we have to observe is that A can't be arbitrary because this parallel transporter object behaves in a certain way under transformations by G. And we can work those out by just looking at the transformation rules. Very interesting, right? You know, we've taken this non-local object, the parallel transporter, and we've built something that looks suspiciously local, right? Because it only depends on a vector of 4 numbers at each space-time location. Not 2 space-time locations, but 1. But of course, there are constraints, and maybe these constraints on A make it trivial again. Well, you know, obviously not. I wouldn't be talking to you about this. I wouldn't waste your time with something that doesn't work. So the interesting thing is, if you apply this whole Taylor's theorem argument to this parallel transport field, then you see that this object here must transform on the left-hand side like this, but on the right-hand side like that. You know, where does this derivative come from? Well, you know, look no further than up here.
Sorry?
Yo.
But how is this derivative defined then? Oh.
That's the normal derivative. I think I've got a missing I, right?
But wasn't alpha just a even non-continuous object?
Ah, yeah, that's true. So this is the moment where we are going to promote alpha from, demote alpha from being independent at all space-time locations to being continuous. At least differentiable one time. Now, maybe you're unhappy with this. You have to impose conditions as they come. Now, even if alpha was differentiable from the start, we still would have had the same ambiguities. Under one of these local gauge transformations, we see that if A mu x transformed in this particular way, then we'd be able to satisfy this constraint here. Or another way of saying it, this condition here requires that A mu transform exactly like this under the local gauge group like this. Okay, I'm not a little bit slightly unhappy with the notation I've used here. I'm going to just rewrite this slightly to make this get rid of potential confusions. So n is just some 4 vector. I think that's now good. Yeah. I prefer to do that because with the unit vector in here, there's some ambiguity with what I wrote there. So I just prefer to do it like this, and it's more general anyway. Right, so if we can find a field A mu of x, a list of 4 numbers per spacetime location that transforms in exactly this way under a gauge transformation, local gauge transformation, then we'd have presented an infinitesimal way to do this, to build this parallel transporter object like that. Let's put this all together inside the definition of the covariant derivative up there. If you use this expression here for the parallel transporter between nearby locations, in the definition of the covariant derivative up here, then you'll arrive at the following expression for this covariant derivative. So it's an exercise. It's an exercise in just substituting in that Taylor series into that formula there. So it's very straightforward. So this is our definition for the covariant derivative. It's just the normal derivative plus this additional term that depends on this extra data a mu on x, which depends on x. Yeah.
In this formula for a mu, this transformation, isn't there an I missing?
Isn't there an I missing? Yeah, I believe there is an I missing. You're right. Thanks. It's here, right? Yeah, minus. Yeah. And then that's correct. Now, this is a purely local object. It depends only on x now. See, it's x, 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 versus having to deal with this parallel transporter for all arbitrary pairs of spacetime location points. And further, it's another exercise to show that this d mu psi of x under one of these gauge transformations transforms in exactly the right way. So you might have been, for finite epsilon, there are an infinite number of terms in the series for the Taylor expansion of u. But in the definition of the derivative, we take that limit to 0, and it turns out only the first order term has any contribution. And you get this expression, and then using this transformation rule here for this gauge field a mu of x, you can just directly show that this transforms in the correct way. And now we've boiled our problem down to finding a field which transforms in this particular way. So I haven't yet quite shown that this all exists, because you need to know, does there exist an a mu that transforms like this? But that's a definition. All right. So this transformation rule here, you can think of as a definition. It's like, how does something transform from one reference frame to another? Yeah, a question?
But do we, understood. We said that this A is defined with the help of U, and we know that U is the parallel transporter. Couldn't we get the A with the help of the mathematical structure that we get over the parallel transport?
Couldn't we, so the question is, could we get A from the mathematical structure of the parallel transporter? Yeah, we could, if we had a parallel transporter to begin with.
Yeah, couldn't we define one?
We could, but I don't know how to do one sort of out off the top of my head. It's possible to look in a math textbook and find an answer. Maybe that's one way of answering that question. Yes, that's certainly possible. But here we want to try and keep things as elementary as possible and not make Hail Marys to math textbooks. So it's instead of just having a parallel transporter given to us by clever mathematicians, let's try and think how we would build a parallel transporter. And this is how we would build one. We would build one by first finding an a mu x, just one assignment of a mu x for all x. And then, under gauge transformations, we define a mu to be given by that expression there. So the gauge transformation is that extra data there. And then we get the parallel transporter by exponentiating this expression here. So we'll go into that a bit later. Right now, I'll just sort of leave it at that. We've managed to build parallel transporters in terms of a local field a mu of x. And it's worth noting that this local field, although it's local here, it depends slightly non-locally on the gauge transformation here. Just slightly. Here, and then a little bit of non-locality there. So what have we got? We've got a way now to define a derivative that transforms in the right way under local gauge transformations. A derivative like object is not the derivative, it's a derivative. And we could just go ahead and build invariant Lagrangians. By every time you want to put down a d mu, you put down a d, a big D, right? And that works. And then what could you do? You could then use this Lagrangian as the basis for a quantum field by quantizing the Dirac field and leaving the a mu alone. Just leave that as some classical thing, some classical background. You could do that, right? That's a perfectly legitimate thing to do. You could leave the a mu, you regard this as the solution to the parallel transport problem, and then you just leave it as a classical fixed quantity defined all around space-time. And then you quantize, you'd have no problems. You can go through, do path integral quantization, whatever you want. But that's not quite in keeping with our goal of explaining everything in the universe, right? Because this a mu is also a field. It's a vector field. And that a mu is presumably an element of reality or something like this. And it should be treated on the equal footing as the original Dirac field. So we should actually quantize it as well, in keeping with our idea that everything in the universe is described by one quantum theory and all the degrees of freedom must be quantum. Then a mu had better be quantized. But to quantize a mu, we have to give it some dynamics. So at the moment, up to this point here, A mu is some static thing, right? Some background helper function. But if you recognize that it's a vector field itself and that you want everything to be quantized, then you ought to really give it some dynamics of its own. And so we now ask the question how to give this A mu some dynamics. Well, we have a nice expression for the parallel transporter. So this is also correct to first order. So if you work out the Taylor series for the parallel transporter, you see that you can actually use a exponential on the right hand side and get exactly the same Taylor series. And we know that this object transforms in a very nice way, right? We know that under gauge transformations it transforms in exactly the right way. So we're going to use this, and we're going to use one more fact to build a derivative for mu, A mu that also transforms in the right way. We're going to use this object in a clever way to build something that is gauge invariant, that doesn't even change under gauge transformations. So I'll tell the story first and then I'll write the math. So u x to x plus epsilon n is the way to move a field at x to x plus epsilon n in such a way that it transforms in just the right way. You move it in as parallel a way as possible is the differential geometric interpretation. Now what happens if we take our field on a little circle, take it on a round trip? Well, we take the field, we're at x, and then we move our field to x plus epsilon x, and then we move it up to x plus epsilon y, and then we move it from there to x plus epsilon y, and all the way back to where we started. So on this round trip, we had to use this parallel transporter to carry out these steps. But we know that what we started with has to transform in the same way as what we ended with, because that's just the way this thing transforms. Now, often enough, this will just be, it's possible to imagine that the result of multiplying these four things around this round trip here, on x plus epsilon in the one direction, x plus epsilon in the one and the two directions, x plus epsilon in the two directions, it's possible to imagine that the result of going around this round trip here is not 1. because there's this field A mu here, which can vary in, well, you know, different ways along these paths here. So the result of going around this round trip here may not be 1. In fact, it will depend on exactly what this A mu is, and it will depend on A mu in a particular way. It will depend on the curvature of A mu. This is how curvature is defined in differential geometry. It's taking round trips and seeing the difference between what happens as you go around the round trip. Or another way of defining curvature is if you go this way and compare things with going this way, do you get the same answer? If you get the same answer, then you're in a nice flat space-time, but if you get a different answer, then you're on some near the North Pole of the sphere or something like this. So this is a way of defining somehow a curvature of this field, and what's more, and what's sort of notable about this quantity is it's gauge invariant. It doesn't depend on the gauge transformation. So the result of doing these multiplications here is actually gauge invariant. It doesn't even depend on G. So it's going to depend on the curvature of this A mu, and it will be gauge invariant. So there will be derivatives of A mu in there, and they will be in a particularly nice way as to be invariant derivatives that we could put in a Lagrangian. So let's actually do all the dirty details. Sometimes there's just no substitute for doing hard work. So now computing, we're just going to multiply all these parallel transporters around. And there's a fourth one. So that's the actual parallel transport action. It's the actual route that we took. We went in the 1 direction for a bit, then we went to the 2 direction for a bit, then we went in the -1 direction for a bit, and then we went in the -2 direction for a bit. And note, U box is gauge invariant. It does not depend at all on G. And it's a super tedious calculation. To do all the Taylor series that come out. But the answer is extremely nice, so it's worth it. Yeah, it's not very beautiful, but something very beautiful will happen. So if we expand in powers of epsilon, then
Should that maybe be a minus in the A2 and the A1 term?
question is, should that be a minus between the A1 and the A2?
There is a minus, but
There is minuses, yes, but maybe I missed out on another. No, there's just that minus. So where is the picture? So we're going A1, A2, and there's probably a minus in front of the A2. has to be very careful at this moment. So these two here are just the standard parallel transports across here and here. And then this next, this A1 here, this term here is corresponding to this parallel transport there. So that's why there's a minus in front of it. And this A2 is the parallel transporter going from here to here. And I do believe there must be a minus in front of it. Unless I made a mistake. So in my notes there's a plus there, but I can't see why there would be a plus for the moment. No, I'm pretty sure that's a minus. So if we expand in powers of epsilon, then what do we get? Well, we can already see from this picture what we're going to get. So to order 1, we get 1, right? To order epsilon, we're going to get 0. Everything cancels to order epsilon. So I need order epsilon squared that we get something. So if you look here, you can already see that at order epsilon, everything cancels. You have to do some more Taylor seriesing to get that. But believe me, it cancels. And then only at order epsilon squared do we actually get something. There it is. That's the result of a lot of Taylor series. Because you've got to Taylor expand this guy, and this one, and this one, and this one. And then confirm that you only get something at order epsilon squared. Oh yeah. Why is it 0 to order epsilon? Well, because the exponent, because we got an epsilon here, so that's the only, this has to be order 1 in here. So you set epsilon to 0, and then you've got, that's where the minus sign is there. Then you've got a2 of x minus a2 of x plus a2 of x minus a1 of x plus a1 of x. Yeah, so that's that minus sign now. I'm much more confident about it. But what have we learned? We've learned that we have something that's gauge invariant and has derivatives of a's in it. So this whole thing transforms trivially under G. Therefore, d1a2 minus d2a1 transforms trivially under G. Thus, and why did we, we did it for going in the x and the y directions, but, well, that was just an example. We could have gone in the x and the z direction, or the t and the z direction, and so on. So we have actually at our disposal 16 possibilities, of which several are trivial, right? If we go in the x direction and then in the minus x direction, that's kind of boring. So we only have 4 choose 2 possibilities. And we're going to label them by the directions that we use, going in the mu and then in the nu. So this quantity here d mu a nu minus d nu a mu, the curvature tensor, this thing is locally gauge invariant. So we've almost done everything we want. We found an object which is invariant under the gauge but has derivatives in there, so A could have some dynamics. Now we have to build a term for our Lagrangian that is invariant under the Poincare group as well. So this is not Poincare invariant, right? There's spacetime indices here. It is a tensor, it's a 2 tensor, so it transforms under the Lorentz group. But of course we know how to build objects that are Lorentz scalars, namely that. And then it's traditional to put minus a quarter in front of it. So now we can build a very non-trivial Lagrangian. And indeed, what we've built is the Lagrangian for quantum electrodynamics. And it's got all the features one would want of a theory. It's, as a classical theory, everything I'm saying is always being classical the whole time. As a classical theory, it's Poincare invariant, right? By construction, everything's contracted properly to a scalar, and additionally, it's also locally gauge invariant. Right? We laboriously showed that that's locally gauge invariant, and now we've also shown that this thing here is locally gauge invariant. This is none other than the action for the electromagnetic field minimally coupled to the Dirac field. Now I could say lots of things about this coupling. It is possible to build more complicated gauge invariant derivatives, but they would not be renormalizable. So that's a common question, like why do we choose the minimal coupling here? Well, one, it's locally gauge invariant, but you could have done it another way. But if you did it another way, it would not be renormalizable. There would be no way to absorb dependencies on the cutoff, but I won't prove that in this course. To finish, I just want to show you an alternative derivation of the gauge invariance of f mu nu. I think that's sort of sufficiently nice. Indeed, it takes only a couple of lines versus these plaquettes and everything. Before I do that, why did I bother? If I showed you this horrible thing, this way of doing the f mu nu with plaquettes and Taylor series and all this nasty stuff, why would I have done that if there's a more elegant derivation? Well, there's a very particular reason, and it's to do with the lattice. So later on, we're going to talk about gauge theory on a lattice. That's the only way that I know of that you can simulate gauge theories on a computer is on a lattice. And to do gauge theory on the lattice, it's extremely convenient to work with these plaquette variables and operators. Whereas to do gauge theory via path integral quantization, it's much more attractive to think of f mu nu as I'm about to derive it. So these two alternative approaches actually suggest two alternative ways of defining this f mu nu, which are more convenient in the context. All right. Well, okay, here's the observation. We know that d mu is gauge invariant. Therefore, the commutator of these two derivatives is gauge invariant. That's how it transforms, right? But the commutator is not a derivative. Partials, right, commute. It's a theorem in many variable calculus. So that's actually 0. Okay, these guys commute, they're just numbers, so it's also gone. It's gone. What are we left with? Well, same thing as before. Cool, huh? So the commutator of the covariant derivative is the curvature tensor. Put it with downstairs indices. Oh, i.e.
Sorry, what about the second terms of the commutator of the derivative and the a's?
What about them?
Because they are not there. You have the derivative of mu of psi multiplied by a mu.
Yes.
I don't see why.
So the question is, why is this equal to this, I guess? Yeah. Because the commutator here, well, I'll put it in here. So let's look at this first commutator here. It's because of the product rule. So the commutator d mu a nu psi is equal to d mu in brackets a nu psi minus a nu d mu psi. But we've got to use the product rule in here. So that is equal to d mu a nu times psi plus a nu d mu psi. But that bit cancels with that, but we're still left with something.
Yeah, I didn't see that.
Yeah. So that's why these commutator expressions here actually lead to something not trivial at the end. All right, so I could have just done that to begin with, but sometimes it's worth, in fact, it's always worth knowing two ways to prove a thing. You never know when it'll pay off. All right, that's it for today. Next week we're going to begin, non-abelian gauge theories. This was all abelian. Okay, thank you very much.